wasn't then. Yeah, it wasn't.
All right.
I haven't used it yet. Probably should. I haven't seen that kind of stuff around it.
Why are you so slow right now?
Guys like.
That wasn't part of the script. It had like 100 billion things to it, so we just got tired, so it just fired.
All right, so we are going to talk about
What was it?
hydrogen as a fuel source. So let's say I wrote hydrogen gas reacting. It would react with, and I'm going to use their example, half a mole. I know. So we have the gas. Okay. The burning or the producing of water here from hydrogen gas has a very, very, very exothermic enthalpy. So the question is, why don't we use hydrogen as a fuel source if it's approximately 3 times, it gives off 3 times more energy per mole, approximately.
That's really good. Increased water is involved.
Yeah. I mean, all of the, uber left-wing naturists, right? They look at this and go, wow, we don't have to, put any more CO2 into our air or whatever. We can just use hydrogen as a fuel source and produce water. I wonder what that would do, though. I feel like over time, wouldn't that like flood the earth? Probably not. Let's assume.
It make it humid.
That's true. But then that water in the air would
Fall in
condensate
Yeah, fall in rain.
and rain.
It'd be raining.
I just don't know. Yeah, that probably wouldn't significantly change anything. Okay?
Unless the carbon dioxide from other cars got mixed with that gas, it's the thing. It's not
Yeah. So I'd probably have some more acid rain. But all right. I'm pretty sure it's when like CO2
Yeah, it's
like bonds or like somehow interacts with the rain.
yeah, it's carbon something after gases and rain.
It's not like it's raining acid. It's just like has like a lower pH than like normal condensation would.
It can eat away at brick and stuff eventually.
Yeah.
But it takes a long time.
All right. So we're going to talk about kind of the reasons or the main reasons why, or the obstacles that we have as to why we haven't been able to harness the fact that it has 3 times more kilojoules of energy per mole than what we currently use, methane or gasoline. Okay? The 3 things we're going to talk about is the cost of production, the storage, and the transportation. Now I'll kind of talk about storage and transportation on kind of the same line of thinking here. But let's start with cost of production. People have been trying all kinds of ways to be able to produce hydrogen gas. And the reason why they have to produce hydrogen gas, guys, is because hydrogen gas just doesn't exist in some amounts naturally in nature, thankfully. Right? I mean, we're probably talking less than, I don't know, 0.01% of the Earth's atmosphere is hydrogen gas. So getting the hydrogen gas out of the air is not like an infinite amount of fuel source. Does that make sense? So we have to produce it somehow. It doesn't just occur naturally like gasoline does, where we can get the oil from the ground. Now that's not necessarily produced naturally, but there's such a large amount of gasoline that we can, or oil that we can get and produce gasoline from. So here are 4 ways that they've tried to use to produce hydrogen gas. Okay? First method, electrolysis of water. Now, what they do with the electrolysis of water is really virtually this. They take really high voltage and just pretty much run it through the water, and it actually separates the water molecule into hydrogen gas and oxygen gas. Okay? We could probably do that. I want to do that. We can do that. Should we do that?
Yeah, then they ignite it.
Yeah.
Big fire.
Test day? When are we gonna have time on test day?
Oh, we did that with plenty of time.
Yeah, plenty of time is there. No big
Yeah, it only
deal.
takes 6
I think I shortened the test 5 questions last year, and it still took them like 3 class periods. So it's gonna take you like 5. Yeah. I had people get them done in 1 class period. Yeah. Kara used to get done with most of hers in 1 class period last year. Tim Draybeck would. Not many.
Just the really.
The guy that's got like a 36 on his DCT.
It's doable, just saying. Alright, second one. Oh, so the reason why the electrolysis of water is not a viable way to produce hydrogen gas is because electricity costs a lot. It takes a lot of electricity. So really, because hydrogen gas doesn't appear naturally in nature, there is a certain amount of expense that just goes in to produce it. So you lose that off the top if you have to produce it versus it being naturally occurring. Okay? Second, thermal decomposition. You can actually heat water up enough, and it will spontaneously decompose. What's the problem with that?
It's expensive to buy the fuel, and it's a lot of energy.
Yeah,
Magnesium,
I mean,
though, if you burn magnesium, it separates water into hydrogen and oxygen, and it explodes. Pour water on magnesium fire?
well, you don't want it to explode.
No, you don't. But like, you have a flint set. It comes with a block of magnesium. You scrape it off and start a fire.
Uh-huh.
But if you light the whole block on fire, you pour water on it. The heat separates it into oxygen and hydrogen, which is burn and explode. It's a little small fireball, but it's really cool.
I don't know if they've tried that.
I looked up on YouTube. I don't know if you have anything, I guess, but it looks pretty real.
Yeah, probably fake, but maybe. I don't know. I don't know. I would assume that if it was a viable option, they would have tried it. But
Well, it ignited it instantaneously because
oh,
of the fire.
oh,
So you can't use it to produce H2.
sure.
You choose it
It just burns the H2 as soon as it creates it.
to. Yeah.
Okay,
So pretty cool.
makes sense. The reason why thermal decomposition really doesn't work is because again, it takes a lot of energy to heat it up high enough to actually get it to decompose. So we're spending money just to get hydrogen gas. Next one, thermochemical decomposition. Let's turn to page 268 for this one. This is the one I probably wouldn't know the least about. 268. Really get a headache with this darn thing. I feel like that hat makes you hotter. It doesn't like protect you from anything. Right, that's just the sun, but that's about it. But like I feel like alright. Where are we? Alright, thermochemical decomposition is going to be kind of the paragraph right above the equations there. Everybody see it? In thermochemical decomposition of water, chemical reactions as well as heat are used to split water into its components. One such system involves the following reactions. The temperature required for each is given in parentheses. Note that the high is not consumed in the net reaction. Note also that the maximum temperature required is 825 degrees Celsius, a temperature that is feasible if a nuclear reactor is used as a heat source. A current research goal is to find a system in which the required temperatures are low enough that sunlight can be used as the energy source. If they could do that, that would probably be a pretty cost-effective way of producing hydrogen
I
gas.
mean, France already uses it. power, they're fine. A lot of places,
I know.
yeah.
Yeah.
It would be.
Okay, but what about the organisms that decompose water without the aid of electricity or high temperatures? In the process of photosynthesis, green plants absorb carbon dioxide and water and use them along with energy from the sun to produce substance needed for growth. This is leading into the next one, which I think is the coolest of all of them, and I would be interested in knowing more about it. Scientists have studied photosynthesis for years, hoping to get answers to humanity's food and energy shortages. At present, much of this research involves attempts to modify the photosynthesis process so that plants will release hydrogen gas from water instead of using the hydrogen to produce a complex compound. So essentially what they're trying to do is genetically modify plants to produce hydrogen gas. Because if you can do that, that's a pretty infinite source of hydrogen gas, what you say? The storage, okay, that gets to the storage. Oh, wait. Okay, so it says small-scale experiments have shown that under certain conditions, plants do produce hydrogen gas, but the yields are far from being commercially useful. What does that simply mean?
It's not practical.
Yeah, it's not producing enough. At this point, the economical production of hydrogen gas remains unrealized. Okay? So, those are the ways that they have been using to try to figure out how to produce hydrogen gas in some feasible way. So they've been able to produce hydrogen gas, but the problem is it costs too much. In all of these examples, or it doesn't produce enough. So, let's continue going on here. What I want you guys to do here, before I do this, let's see here, what do I got here? Do I leave space anywhere? Fine. I was going to have you do the equation for using methane to produce hydrogen gas, but we won't do that. All right. So storage and transportation issues. Okay. Here's the storage and transportation issues. Believe it or not, hydrogen gas, when it's being enclosed by a metal chamber, like if you were to pump hydrogen gas through metal pipes, or you were to transport hydrogen gas in those big metal trucks, you know, those gasoline trucks that they carry fuel in. Hydrogen is actually quite interesting because it's so very, very small. When it gets to the surface of the metal, it actually breaks up into its individual atoms. So instead of being H2, it breaks up into hydrogen, just a hydrogen atom. Well, that hydrogen atom, since it's so small, can actually migrate into the metal. And that actually causes it to be very, very brittle. So you can imagine the problems of trying to pump hydrogen gas through pipes. You probably have to do it under relatively high pressure, on top of the fact that it already migrates into the metal and makes the metal weak, and it could result in what? Collapse of the metal. Yeah, you wouldn't want a whole bunch of hydrogen gas all of a sudden just flying out.
But yeah, it's flammable.
Okay? No, it would be awful. Okay, well you're probably thinking, well, why not? Why not then just liquefy it and do it that way? Well, let's talk about that. But before we do that, let's try to figure out volume here and how the volume can play a part in being able to transport and store this. It says compare the energies available from the combustion of a given volume of methane and hydrogen gas at the same temperature and pressure. Okay, so let's see, hydrogen gas and methane gas. So here it is, approximately the kilojoules per gram. hydrogen gas, and this is approximately the energy per gram of methane. Okay, what I want to do here is I want to take this and I want to convert it per mole. Because we know there's a relationship between moles and volume, right? Anyone know what that relationship is? Say that louder. 22.4. So if I know per mole, if I got a mole of hydrogen gas and I have a mole of methane gas, it occupies 22.4. So let's take this and let's convert it to moles. 2.02 grams for every 1 mole. Once you guys do that, calculators out, get you doing something. And then, what's that one? 12 plus 4, 16.05. One here in calculators.
Why would it be times 2.02? I know it cancels the units, but you already have it per gram. Why would you multiply it by it? Oh, it's just not in grams. Never mind. Because it was in grams to divide, but it's not per gram. Never mind.
Per gram. Yeah. I know how much energy per gram I have. I want to know how much energy per mole I have. And you're going to see a significant change in per gram versus per mole. What is the kilojoules per mole of hydrogen gas? Every 1 mole. Okay? How about methane? So you can see we went from something that was 3 times more effective per gram, but became 3 times less effective from a volume standpoint per mole. So you could say that, what, a 1 to 3 relationship, which means to get the same amount of kilojoules per mole as this, I would have to have about 3 times the volume of hydrogen gas that I would need for methane. That becomes a storage issue, that becomes a transportation issue, that becomes a cost issue. Okay? Per mole, if I want to get the same energy per mole of hydrogen gas, I would have to have 3 times the amount to get the same energy. So therefore, I'd have to have 22.4 times 3 more than I would for methane. Does that make sense? What was that? No, because gas is dependent upon how many moles you have on your mass. So, okay. All right, let's get to this last thing, which I think is really interesting to kind of show this. It really kind of puts in perspective the difference, the decrease or the difficulties we have in transportation and storage for comparing methane to hydrogen gas. And this should be the thing that should kind of blow your mind a little bit. Look at the differences in density. So hydrogen's not very closely packed together in comparison to methane. Okay? So here's what it's asking. Okay, so we're going to assume that the combustion of hydrogen gas provides 3 times as much energy per gram, which is what we said. Calculate the volume of liquid H2 required to furnish the energy contained in 80 liters of gasoline. Calculate also the volume that this hydrogen gas would occupy at 1 atmosphere and 25 degrees Celsius. So what we probably need to do first is figure out how many grams of methane are in 80 liters of methane. How do we go about doing that?
So that would be 22.4.
Well, I'm not so sure we're not at STP, we're in standard state. How would I do it? How would I get from
I use density.
Oh, yeah.
use density? Okay, I know the density of my gas. Now I am going to need to take this and convert it to what? Milliliters first. Following so far? Density? So we get crazy. 59,200 grams are in 80 liters of methane from gasoline. Okay? Great. Why did I do that? What am I going to do with that now? You're on the right track, Annie. You're on the right track. We'll do that later. You said something about this. We know that I can get the same amount of energy with a third less mass, right? Because, right, if hydrogen gas is 3 times more effective per gram, you could take this number divided by 3 and get the same amount of energy out of it in hydrogen gas, correct? Does that make sense, everyone? So this is how many grams of hydrogen gas, or that's how many grams of hydrogen in our liquid form we would need. Because this is going to be liquid, I think it says, doesn't it? I think like the volume of liquid hydrogen, yeah. Okay? So, how would I figure out how much? Yep. Not near as dense. Now I'm going to take that and convert it to liters because that makes a little bit more comparable sense. So 277 liters of liquid hydrogen. Now this should make sense because it was approximately 3 times the moles. It's approximately 3 times the volume here. A little more than 3 times. If you compare 80 to 280. Okay? Now that is liquid hydrogen. Is it easy for us to get hydrogen gas to liquid form? No, not easy at all. Okay, so let's take this amount here, and let's try to figure out how much volume that would be in gas form. Would be a lot more, right? Because gasoline is naturally in its what form? Liquid form, right? Hydrogen gas is naturally in its gaseous form. So let's see, let's compare then the same amount of energy that we would give off per liquid gasoline in comparison to gaseous hydrogen gas. So I'm probably going to need to get this into what form? Moles. Let's do it. Can I erase this up here? Okay, when you do that, the mole number is okay, great. Why did I get moles? What am I going to do with that? How am I going to figure out how am I going to figure out the volume of this gas? Ah, yes. I didn't think you guys would get that. Good job, Grant. Ideal gas log. I got pressure, I got a temperature. The volume would be nRT over P. Why don't you guys solve that? You guys do remember the R, yeah? What do we get? Grant?
238,541.
238,000 what?
541.
All right. So, per gram, hydrogen gas is pretty darn awesome. But problem is hydrogen gas exists in gas naturally, and gasoline is liquid naturally. So to get the same amount of energy output, I would need way more volume to hold it. Could you imagine how many tanker trucks that would take to transport the same amount of energy across the country?
It's that opposed to 80.
Yeah. Because, but remember, the 80 liters is liquid gas. So it should be a lot more volume because it's in the gaseous form for hydrogen gas. And the fact that it's not very dense. So you're seeing that really, at least from my perspective, it seems like at this point, hydrogen gas is really not a feasible option. Probably why we haven't been using it. Okay? If they could even somehow come up with plants that could produce hydrogen gas like crazy, we've just overcome the cost problem. We still have to deal with the transportation and storage problem. Not gonna be able to put them. You're not going to be able to put them in lead pipes and transport them underground or above ground because of the fact that hydrogen gas is so small and can get in between the metal. Maybe if they find a cost-effective way, then maybe they can look into some material that doesn't corrode or doesn't break down or get brittle, and they can transport it that way. But you're certainly not going to pump this into a tanker truck and send it across the country, are you? You would need like like 1,000 more tanker trucks to do the same amount of, get the same amount of energy across the country as you would if you were just pumping it in methane form. All right, we're done.